Hey guys, in this video lecture we will be discussing your class 10 mathematics exercise 1.1. So let's begin with the first question. Use Euclid's division algorithm to find the HCF of, you need to find the HCF of 135 and 225, and you have been given two more questions. So let's begin with the first one. So our first question is 135 and 225. We need to find the HCF of both the numbers, and we need to use Euclid's division algorithm to find the HCF. So let's begin with the solution. So 225 is greater than 135. So since 235 is greater than 135, here we will take 135 as the divisor and we will divide 225. Means 225 is our dividend and 135 is our divisor. Now 135 1 135, and here you'll get the remainder as 90 and your quotient is 1. Okay, so you can easily write it over here since we got it like this. So you can write, like, as we know, dividend is equals to divisor into quotient plus remainder. So 225 will be equals to, divisor is 135 into quotient is 1 plus your remainder over here is 90. Okay, since the remainder is not equals to 0, since our remainder, that is 90, is not equals to 0, we need to move further. Okay, now what we will do, we will take our new divisor as 90. We will consider our new divisor as 90. Why 90? Because 90 is the remainder. Okay, let's do it like that. Okay, so our new divisor will be 90 and our dividend will now become 135. So 135 divided by 90. Okay, we'll do it like this. So we'll get 190 1 90, and here you'll get the remainder as 45. See, again here the remainder is not equals to 0, so we need to move to further steps as well. But here again you can write it like this, like dividend is equals to divisor into quotient plus remainder. So 135 will be equals to, divisor is 90 into quotient 1 plus remainder, that is 45. Again, since 45 is not equals to 0, means our remainder is not equals to 0, we need to divide it again, and in this case again our new divisor will be the previous remainder. The previous remainder was 45, and the last divisor, that means 90, will be our dividend right now. So 45 2 90. So now in this case you get the remainder as 0. So as we got the remainder as 0, so we will stop right here. Now what we had to find, we had to find the HCF, right? We need to find the HCF. So now what will be the HCF? What will be the HCF? HCF will be equals to 45. Why 45? Because the last divisor was 45, by which we got the remainder as 0. That's why HCF will be equals to 45. So how will you write this thing? You'll write it as HCF of 135 and 225 is equals to 45. So it's very clear till here. Okay, now we'll move to the next question. So our next question is this one, 196 and 38220. We need to find the HCF again, and using Euclid's division algorithm. The same way we'll proceed. So here, since 38220 is greater than 196, here our divisor will be, here our divisor will be 196 and our dividend will be equals to 38220. Okay, so let's divide 196, 1 jar 196, and here you will get 6 8 1. Here taking this 2 down, will again multiply 196. If we multiply 196 by 9, you'll get 1764. So this is the nearest one, 1764, and again cancelling them out, we got here, and again taking this 0 down, we got 980. So 196 into 5 will be equals to 980. So 196 into 5 will be equals to 980, and here we got the remainder as 0. Erasing this rough work. Okay, so since here we got the remainder as 0, we need not perform any other, we don't need to perform any other further division. So here the divisor was 196 and the dividend was 38220. Quotient we got 195 and remainder is 0. So what we can do, since the remainder here is equals to 0, so the remainder the HCF that we actually need to find, the HCF of both the numbers 196 and 38220 is always the divisor by which we got the remainder 0. So what is the divisor by which we got the remainder 0? Is 196. It's very easy. Okay, so the answer is 196. Let's move to the next one. So our next question is this one, 867 and 225. So we begin with the solution. Since we know that 867 is greater than 255, so our divisor here will be, so our divisor here will be 255 and our dividend will be 867. Dividing both of them. Okay, so how will we divide? We will perform the rough work over here. 255 into 3, 765. Okay, so 3 jar 255, 3 jar 765 we got over here, and if we will get here 102. So here the remainder is not equals to 0. So what we will write over here, dividend means 867 will be equals to divisor, that is 255, into quotient, that is 3, plus remainder, that is 102. Now since the remainder is not 0, we need to move further. We'll again divide it. Okay, so let's do that thing. Okay, we'll divide it again. So what will be our new divisor? The previous remainder becomes our new divisor, that means 102. And what will be our new dividend? The previous divisor becomes our new dividend, that means 255. Okay, so 102 into 2, 204. So 2 ja 204, and here we will get the remainder as 51. So again the remainder is not equals to 0. Here again the remainder is not equals to 0. So we again need to move further, means we again need to divide. So again how we will write over here, that means the dividend means 255 will be equals to divisor 102 into quotient 2 plus remainder that came here 51. Okay, so it's clear till here. Now again, since the remainder is not equal to 0, we need to move further and we need to divide it again. So what will be our new divisor? The previous remainder, that is 51, will be our new divisor. What will be our dividend? 102. So 102 became our new dividend. So 2 ja 102, and if we got the remainder here as 0. Now since the remainder is 0, we don't need to move or perform any further steps, and this is the final division. So we can write it over here that the HCF of both the numbers, that is 867 and 255, will be equals to what? The last divisor by which we got the remainder 0, and that is 51. So the HCF is 51. Let's move to the next question. Okay, so the next question is, show that any positive odd integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. Okay, so let's begin with the solution, or let's begin with the proof. We'll consider a as any positive integer. Let a be any positive integer, and since we know that a is equals to bq plus r, by Euclid's division lemma we know that a is equals to bq plus r. So here you can see that 6q plus 1 is there, 6q plus 3 is there, and 6q plus 5 is there. So b is definitely 6. Okay, so we'll also consider, let a be any positive integer and b equals to 6. We are considering b as 6, and then q will be greater than or equal to 0. Your quotient can never be negative, right? Your value of q should always be greater than and equal to 0. And there was one more condition for this Euclid's division lemma, if you remember it properly, that a is equals to bq plus r was the Euclid's division lemma, and the condition was that value of r should be greater than or equal to 0, and it should be less than b. That means here the value of r should be less than 6, since the value of b is 6. So what are the possible values for r? What are the all possible values for r? The values of r can be 0, 1, 2, 3, 4, 5 and 6. These all, sorry, it cannot be 6 because it should be less than 6, so it's still 5 only. So the possible values of r are 0, 1, 2, 3, 4, 5. Okay. Now putting the value of r in this equation, and we'll put the value of b as 6, and r one by one we'll put the value of r. So what will we get the values of a? A will be equals to 6q when the value of r is 0. A will be equals to 6q plus 1 or 6q plus 2 or 6q plus 3 or 6 cube plus 4 or 6 cube plus 5, since the value of b is 6 and the values of r are these. Okay, now moving forward, see, this 6 is an even number. Okay, and any number multiplied by an even number is always even, means regardless of the value of q will get the value of this 6q as even only. Okay, this 6q is again an even number and this 1 is odd. Here again this 6q is even and this is even, this is even, this is odd, this is even, this is even, this 6q is even and this 5 is odd. So even plus odd is always odd, even plus even is always even, even plus odd is again odd, even plus even is even, even plus odd is odd. So what are the outcomes for odd? Here we got one odd and one more odd. So 6q plus 1 we got here, 6q plus 3 we got one more odd, and 6q plus 5 we got our third odd number. Okay, so hence it is proven that since any positive for any positive odd integer it is always of the form 6q plus 1, 6q plus 3 and 6q plus 5. Okay, so the next question that we have been given over here is that an army contingent of 616 members is to march behind an army band of 32 members. Means there are certain number of members in an army contingent, that is 616 members, and these 616 members have to march behind these 32 members. The two groups are to march in the same number of columns, mean the number of columns should be same. What is the maximum number of columns in which they can march? So we have to find the number of columns and the maximum number of columns in which they can march. So here students, the most important thing that you have to notice is that you have to find the maximum number of columns. It means you have to find the HCF. Whenever you have to find the maximum of something, there you have to find the HCF, and if you have been asked to find the minimum of something, then in that case you will have to find the LCM. Okay, so here we'll have to find the HCF of 616 and 32. So we'll find it by Euclid's division lemma. So it's we have done that before also. So using Euclid's division lemma, we can write it as 616 is greater than 32. So dividing 616 by 32, what we will get? 32 1 ja 32, and here you will get it as 29. Taking this 6 down, you will get as 9 ja 32 into 9 will give you the result as 288. So here you will get 288 and the remainder will be 8. So again you can notice over here that the remainder is not equals to 0, and since the remainder is not equals to 0, we'll again have to divide it further. So before dividing it, you can write it as dividend is equals to division into quotient plus remainder. So 616 will be equals to 32 into quotient is 19 plus remainder is r. Now dividing it further, our new divisor will be 8 and our new dividend will be our previous divisor, that is 32, and 8 4 ja 32. So we got the remainder over here as 0. So Our HCF, since the remainder is 0, we don't need to perform any other further division. So our HCF of 616 and 32 will be the last divisor by which we got the remainder as 0, and the last divisor is 8, so we will get here as 8. So 8 is the number of columns that maximum number of columns that we need to find. Okay, so now let's move on to the next question. So next question is, use Euclid's division lemma to show that the square of any positive integer is of the form 3m or 3m plus 1 for some integer m. So let's begin with the solution. Let a be any positive integer and the value of b will be equals to 3. Why? We know that a is equals to bq plus r, so here 3 is the value of b, and we will consider it as 3. Then since a is equals to bq plus r, so we'll get it here that a is equals to 3q plus r, and for some value of q that is always greater than or equal to 0. Now we also know that for Euclid's division lemma there exists a condition that is the value of r should be greater than or equal to 0 and it should be less than b. That means here it should be less than 3. So the possible values for r can be 0, 1 and 2, because it can always be less than 3 only. Therefore, putting this value of r in this equation, what we will get? A is equals to, since when the value of r is 0, we will get it as 3q, or when the value of r is 1, we will get it as 3q plus 1, or we will get it as 3q plus 2, right? Now what we need to find? We need to show that the square of any positive integer, means we need to square on both the sides. That means we'll get a square is equals to 3q whole square, or 3q plus 1 whole square, or 3q plus 2 whole square. So here you can write this as 3q whole square means 9q square. That means you can write it as 3 into 3q square. Okay, coming to this one, a plus b whole square is equals to a square means plus b square plus 2ab plus b square, that is 1. Taking 3 common out of them, that is if you take 3 common out of them, so you will get here 2q. From these two I took 3 common, and this 1 I am writing as it is. Okay, now for this one what we can do, again this is a plus b ka whole square, that means you'll get here 9q square means a square plus 12q plus 4. Now you can write it as 3 into 3q square. Here this 4 can be written as 3 plus 1, right? So writing this 4 as 3 plus 1 and taking this 3 also common. This 3 is also taken common with these two. So you will get here 4q taking 3 common, and this 3 if taken common will get here 1 within bracket, and this 1 remains, so we'll write it outside. Okay, so see, here you can identify that this 3q square, if taken as a constant, k1. This 3q square plus 2q, if taken as a constant, k2, and if this one taken as a constant, k3, then you can say for any positive integer, means if this, so here you can say that this is of the form 3q, this one is of the form this is of the form, not 3q guys, this is of the form 3m, okay, and then this one is of the form 3m plus 1, okay, and this one again is of the form 3m plus 1. So we can write it as, for any, if we square any positive integer, it is of the form 3m or 3m plus 1 for any integer m. So now our next question is, use Euclid's division lemma to show that the cube, in the previous question we were dealing with the square, and now we have to show that the cube of any positive integer is either of the form 9m, 9m plus 1 or 9m plus 8. So again we will proceed in the same way. Let a be any positive integer and the value of b here will be 3. Then you will get here that by Euclid's division lemma, a is equals to bq plus r, and the value of b, since we have considered here as 3, so it will be equals to a is equals to 3q plus r, where q is greater than equal to 0, and since the value of r should be greater than 0 and less than b, that means it should be less than 3. So the possible values for r are 0, 1 and 2. Now putting these values of r in this equation, we'll get what we will get, that a is equals to 3q when the value of r is 0, or you can get a is equals to 3q plus 1, or you can also get a is equals to 3q plus 2. Now since we have to find the cube of the numbers, we will cube on both sides. So cubing on both sides, we will get a cube will be equals to 3 cubes ka whole cube, that means you will get 27 cube, and that will again be equal to 9 into, like this way you can write it, sorry not this way, this cube should be inside only, and this, considering this as m, you can write it as 9m, okay. Cubing these two, you'll get a cube will be equals to 3q plus 1 whole cube, and that will give you a cube means 27 cube plus 3a square b, that means 27q square plus 3ab square, that means 9q plus b cube, that is 1. Taking 9 common among these three, taking 9 common, you will get here 3q cube plus 3q square plus q, and keeping this one outside itself. Okay, now moving to the next one, cubing this as well. A cube will be equals to 3q plus 2 whole cube. That will give you 27q cube a cube plus 3a square b, that is 54q square plus 3ab square, that is 36q plus b cube, that is 8. Now again taking 9 common from these three, he'll get 3q cube plus 6q square plus 4q, and keeping this 8 outside. Now considering this as a constant m, considering this again as a constant m, you will notice that this one is of the form 9m plus 1, and this is of the form 9m plus 8, and this was of course of the form 9m. So we noticed that the cube of any positive integer is either of the form 9m or 9m plus 1 or 9m plus 8. Thank you.